Today we're working on exponential modeling. This is Algebra 2, review number 6, and you should be on page 17 in your packet. This page right here comes out of our Unit 7 and 8 packet. These are all of the different formulas that you should be comfortable working with. So now let's go take a look at our packet, current packet. Page 17. Number 1, if a population of fruit flies is increasing at a rate of 22.5% per hour, if the population had an original size of 10 flies, which of the following would be its size after 1 day? So because this is just increasing at a rate per hour, and they're asking about hours, you don't have to do any strange manipulations. This is just the simple interest rate. So here's our R. And remember, you have to move the decimal 2 places to the left. So it's 0.225. Here's our original size. That's our p-value. And the last thing they want to know as far as time goes, 1 day is 24 hours. Remember, this is increasing per hour. So now to figure this out, you could just say A of 24 equals 10 times 1 plus 0.225, and then our exponent is raised to the 24. And when you put that in your calculator, you get 1,304 flies gross. Number 2, this is using the same formula, except this time it's a decreasing function. The water level in a draining reservoir is changing such that the depth of the water decreases by 7.5% per hour. So that is our rate, and it's a negative 0.075. If the water starts at a depth of 45 feet, starting as our p-value, then which of the following functions properly models the depth, d, as a function of time in hours since it started draining? So now instead of a of t, they're just using d. So our starting number is 45, and this is 1 minus 0.075 to the t. And they don't have that option, 1 minus 0.075, so we actually have to figure that out. 1 minus 0.075 is 0.925. So make sure you carefully read the problem for increasing or decreasing and take that extra second to write out that rate. Number 3, these are always tricky. It's multiple choice and they want to know which one is not correct. A collector purchased an antique vase. An equation to represent the value A of the antique vase after M months of ownership is that thing in green. Which of the following statements is false, not correct? So what we're going to do is look at each statement. So to save a little bit of time, I just copied that equation in green and I made it a little bit bigger. So this is talking about months. Keep that in mind. Number 1, the value of the vase when it was purchased was $5,000. That's our initial. That is true. The vase gains approximately 24% of its value each month. In looking at this, you might say, sure, the rate is 0.24, so that's 24%. But the problem is, it's not just a simple exponent out here. In order to find out what our true monthly rate is, we need to get rid of this 12. So what we practiced doing during the year is we do 1.24, and then we raise it to the 1/12, because remember there's an invisible 1 there, and then the m goes on the outside. So my equivalent function, 1.24 to the 12th is 1.018. So the actual rate is 1.8%. So this thing is actually your yearly rate. So that's false. That's our answer, but let's just keep going for the sake of understanding. The vase increases in worth by approximately 2% of its value each month. Yeah, it's like 1.8%, so that's kind of close enough. And the value of the vase 1 year after it was purchased is $6,200. A couple different ways you could do this. You could use your starting equation that's inside of this right here. I'm going to plug in 12 months. If you put a 12 in up in this equation and the starting one, you get the same answer. So I got, I'm running out of room. Let's say about $6,200. 6193. I'd say that's close enough. These are tricky because they're written so that everything seems correct. Number 4, the temperature of a cooling liquid in a room held at a constant 75 degrees Fahrenheit can be described by that crazy equation. F is the Fahrenheit temperature and T is the amount of time it has been cooling in minutes. Which of the following was the original temperature of the liquid when it began cooling? So an original temperature means the time is 0. So all I'm going to do is plug a 0 in here. F of 0, wherever you see a T. And then you carefully put that in your calculator and you get 207. So it was about 207 degrees. Number 5, the Speedy Foot Shop, thought it was food, has been selling a newly designed skateboard. The board has been very popular and the shop has seen a 4.25% increase in profits over the past year. If this trend continues, which expression could be used to approximate the monthly percent interest in profits after M months? So for starters, we're just looking at rates. So this A and P value, we don't really care about. So my rate is 1 plus 0.0425. And even though it's weird, I'm going to use a Y here because we're talking about years. 4.25% increase in profits over the past year. We're not compounding. It doesn't say compounded monthly. They just want to know after a certain number of months. So this all stays the same. You don't even have to write this part. This is 1.0425. Now we have to do a conversion, a time conversion from years to months. Because our time goes from bigger to smaller, our new exponent is going to be a fraction. So what I'm going to do is write 1 over 12, and instead of my Y value, this becomes M for months. And now to figure out what our actual rate is, I'm going to do 1.0425 raised to the 1/12. Need an extra parentheses. And then our M goes on the outside. So what you get is whatever your starting amount was, and this new base is 1.00347 to the M. So our new rate is right there. Working with time is extra complicated. So now on page 18, try problem 6 and then check back on the next video and see how you did.